What is going on, guys? Welcome back to another video. So in this one, I thought we'd take a look at this blog post that was released just a few days ago by NetFlix. And so they've basically taken inspiration from this LLM, I don't know if we can call it hype, this LLM for 3 years trend of being incredibly unstoppable. And so they wanted to join in. And basically they wrote a blog post of, what exactly, what are the challenges they face currently and how do they think it can be solved? What are the sort of methods they used? And so I thought it would be really interesting for us to take a look and dive in and try to understand, this from what they have, a really complex recommender system and how it works with this new approach that they're wanting to introduce. So the title is Foundation Model for Personalized Recommendation. So basically, actually, we'll just read through it and then we can get, I'll share my thoughts as we go through. So the motivation: Netflix personalized recommender system is a complex system, boasting a variety of specialized machine learning models, each catering to distinct needs, including continue watching and today's top pick for you. However, as we expanded our set of personalization algorithms to meet increasing business needs, maintenance of the recommender system became quite costly. Furthermore, it was difficult to transfer innovations from one model to another, given that most are independently trained despite using common data sources. This scenario underscored the need for a new recommender system architecture where member preference learning is centralized, enhancing accessibility and utility across different models. So, many of these companies, they want to do many different tasks, right? Example, like Tesla, they need to do lane prediction, need to do road sign, and a lot of these kind of share fundamental embeddings. So an idea is you can use these like HydroNet, where you do a shared across at the bottom, and then you can predict different things at the top, right? In many cases, that doesn't really work as well as if they just do like a very specialized model. And so that's what they typically do. But then it comes costly, as they say, because they have I don't know how many, but let's say 100 different models predicting different things. And then each of them have to be maintained, each of them have to be fine-tuned, and you can imagine all the stuff they have to do, right? So this is in contrast, right, to LLMs, which is performing extremely well, but it's trained on pretty much one task and it's trained in one model, right? So it's like a huge model that's trained on a huge amount of data. So basically that's their motivation. Let's continue. Particularly, these models predominantly extract features from members' recent interaction histories on the platform, yet many are confined to a brief temporal window due to constraints in serving latency or training costs. This limitation has inspired us to develop a foundation model for recommendation. This model aims to assimilate information both from members' comprehensive interaction histories and our content at a very large scale. It facilitates the distribution of these learnings to other models, either through shared model weights for fine-tuning or directly through embeddings. The impetus for constructing a foundational recommendation model is based on the paradigm shift in NLP to large language models. In NLP, the trend is moving away from numerous small specialized models towards a single large language model that can perform a variety of tasks, either directly or with minimal fine-tuning. Key insights from this shift is a data-centric approach, shifting focus from model-centric strategies which heavily rely on feature engineering to a data-centric one. This approach prioritizes the accumulation of large-scale, high-quality data, and where feasible aims for end-to-end learning. So yeah, this is today it still exists, model-centric strategies of having a very specialized model on very specific data and that you fine-tune. That still works, but in general, in many cases, an LLM that's been trained on a huge amount of data can outperform in many cases just because of the amount of data, the sheer data that it's been trained on, and the size of the model. So the two, leveraging semi-supervised learning, the next token prediction objective in LLMs has proven remarkably effective. It enables large-scale semi-supervised learning using unlabeled data while also equipping the model with a surprisingly deep understanding of world knowledge. So yeah, like I think generally here, leveraging semi-supervised learning, basically we want to use unlabeled and labeled data. And so generally we would fine tune it on the labeled data. We would find a way to utilize that unlabeled data in some way. For LLMs, I think that's basically, you know, we use self-supervised learning. So we take all this text data and we ask it to predict the next token. And then we would later on, you know, do more specific fine tuning of like exactly how we want it to behave and so on. So I think that's what they refer to when they say semi-supervised learning here for LLMs. But might be a bit wrong there, not sure. These insights have shaped the design of our foundation model, enabling a transition from maintaining numerous small, specialized models to building a scalable, efficient system. By scaling up semi-supervised training data and model parameters, we aim to develop a model that not only meets current needs, but also adapts dynamically to evolving demands, ensuring sustainable innovation and resource efficiency. So I think this makes it a little bit clearer actually what they mean. So like in their case for Netflix, the label data is the movies that they have. And so they have some movies, right, that they've already got a lot of training data on. But then, you know, every other day or whatever, new movies come out. And so they have to adapt to this new. And that's what I think what they mean by semi-supervised learning, right? They have this bunch of label data for movies that are old or not new. And then they have new movies which are unlabeled data because nobody has watched those movies. So at Netflix, user engagement spans a wide spectrum from casual browsing to committed movie watching. With over 300 million users at the end of 2024, this translates into hundreds of billions of interaction, an immense data set comparable in scale to the token volume of large language models. However, as in LLMs, the quality of data often outweigh its sheer volume. To harness this data effectively, we employ a process of interaction tokenization, ensuring meaningful events are identified and redundancies are minimized. So like obviously for next token prediction, the data is kind of there already, right? Like we just want to predict the next token. In their case, like they need to think of a smart way to distill this data so that the model can actually use that and predict the next token, right? And so I think they'll get to like exactly why that is. But they have, you know, I can imagine Netflix in this case has a lot of data to train on. They say hundreds of billions of interactions. So tokenizing user interactions. Not all raw user actions contribute equally to understanding preferences. Tokenizations help define what constitutes a meaningful token in a sequence. Drawing an analogy to byte pairing coding, we can think of tokenization as merging adjacent actions to form new higher level tokens. However, unlike language tokenization, creating these new tokens require careful consideration of what information to retain. For instance, the total watch duration might need to be summed or engagement types aggregated to preserve critical details. So like you can imagine like here, for example, if they have some interaction history, perhaps, you know, they have all this information, you know, they maybe played this, maybe they paused it, maybe they then scrolled back and they have, you know, they liked that. And so they might have like 10 different things of this particular movie of data, right? What is it that's important for them? What do they actually want to preserve? And like here, for example, maybe they watch this series for like, I don't know, 10 days straight. And so maybe they have like 30 different plays of this episode, like 30 episodes in 10 days or something, right? Then they need to consolidate that into something that is more compressed, but still maintains all the vital information that the model might need. So like the tokenization part in their case is basically how do they summarize the history that they want to later predict. So this trade-off between granular data and sequence compression is akin to the balance in LLMs between vocabulary size and context window. In our case, the goal is to balance the length of interaction history against the level of detail retained in individual tokens. Overly lossy tokenization risks losing valuable signals, while too granular a sequence can exceed practical limits on processing time and memory. So like this is also one thing that's different for them, right? They have to actually think about, well, we're going to deploy this. So like in some cases, the user might click on something and like, I don't know if they need real time in any case, actually. For searching probably, right? So for searching, they need it, right? So when they search for a title, they can't have that cache, right? Because the user might write a lot of different stuff, right? So in that case, I think, you know, and generally perhaps also there's a lot of like real-time stuff that they might need to do. So they really need to think about having sort of fast inference speeds compared to perhaps LLMs, which can be a bit slower. Even with such strategies, interaction histories from active users can span thousands of events, exceeding the capacity of transformer models with standard self-attention layers. In recommendation systems, context windows during inference are often limited to hundreds of events, not due to model capability, but because these services typically require millisecond level latency. This constraint is more stringent than what is typical in LLM applications, where longer inference speeds are more tolerable. So actually, I'm not sure, like I tried to think about this now too, which is where exactly do they need this fast inference speed? Because it seems to me like in many cases, Netflix can pass with using a much larger model and just generate pre-trained or sort of like on a daily basis, you know, run it like X times a day or once a day or something like this, and then have a large model. And then like for very specific niche of search, for example, they might have a smaller embedding model or something. So I'm not sure where they need this millisecond level latency. That seems a little bit like too strict, I would say. I think like if you look at YouTube, for example, YouTube does not change their recommendations that often, right? So like for YouTube, when do they actually need millisecond level latency? Probably only when search. Or I guess like sometimes they also need it, right? Like if I would click on some video, I need to find related videos that they want to be able to personalize to me specifically and not just on a global level. Then they might need to do some inference, right? But those are more niche situations, I would say, more than the general case of just like the homepage. All right, to address this during training, we implement two key solutions. So they use sparse attention mechanisms. All right, we don't have to go through this. Basically, they just compress the attention matrices, right? And that makes sense. So they just use less precision, but they get like maintain computational efficiency. And then sliding window sampling. So instead of taking like all thousands and thousands of interactions for a particular user, they just sample a lot of like spaces, right? So during training, we sample overlapping windows of interactions from the full sequence. This ensures the model is exposed to different segments of the user's history over multiple epochs, allowing it to learn from the entire sequence without requiring an impractically large context window. And I think in this case also, like in some cases, right, we kind of don't really need the entire, like what I watched 1 year ago is not too relevant, right? We can probably use that information in some way to learn an embedding of me as a user that we can then use later on for that specific sort of context of the latest 30 ones I watched, for example, right? I think, you know, the diminishing returns of going through in history of what I've watched, other than learning and embedding, it has quite diminishing returns, right? So I think this sliding window sampling makes a lot of sense for them. At inference time, when multi-step decoding is needed, we can deploy KV caching to efficiently reuse past computations and maintain low latency. So yeah, if they need to predict multiple, there's no need to recalculate all the attention that was used for each time step, right? These approaches collectively allow us to balance the need for detailed long-term interaction modeling with the practical constraints of model training and inference, enhancing both the precision and scalability of our recommendation system. Let's see, information in each token. While the first part of our tokenization process focuses on structuring sequences of interactions, The next critical step is defining the rich information contained within each token. Unlike LLMs, which typically rely on a single embedding space to represent input tokens, our interaction events are packed with heterogeneous details. These include attributes of actions such as locale, time, duration, and device type, as well as information about the content such as item ID, metadata, genre, release country. Most of these features, especially categorical ones, are directly embedded within the model, embracing an end-to-end learning approach. However, certain features require special attention. For example, timestamps need additional processing to capture both absolute and relative notions of time, with absolute time being particularly important for understanding time-sensitive behaviors. Yeah, so that makes a lot of sense for them, right? Like for text, you can reuse the same embedding space. But in this case, if we're talking about, a genre might need to go through some specific type of embedding, same as for the time. The device type, perhaps there are like 10 different devices people can log in from or something, and you need an embedding for each, right? So like you need to think about that a lot, like how should we represent each of these important information in an actual embedding. To enhance prediction accuracy in sequential recommendation system, we organize token features into two categories. Request time features. These are features available at the moment of prediction, such as login time, device, or location. Post-action features. These are details available after an interaction has occurred, such as the specific show interacted with or the duration of the interaction. So I guess you can't kind of mix these, I guess. Perhaps if they log in from, perhaps the time is important for what to recommend. Perhaps the device is important. So if they log in from a phone versus a laptop versus the TV, might be different occasions. And so they want to separate those in some way because they might be important as to when they want to actually do the inference. Yeah, perhaps I think that kind of makes sense. I don't know if it makes that big of a difference. Like I might be misunderstanding exactly why they split these two, but I don't know if I want to recommend different things if you're logging in on a laptop versus on your TV. Maybe I want to, right? Or if you're logging in at lunchtime versus at night. Maybe those are different occasions. And then maybe if we go back, maybe then it also makes sense that they would want to have this millisecond latency. All right, so I think we might need to, a little bit more insight. It's a bit difficult to figure out exactly why they split them into these two. The only thing I can think of is like this would then change the next sort of action we want, right? So this is important pre-knowledge that we want, and we can't sort of combine them in some meaningful way. But I can imagine that there's multiple ways you can actually do this sort of modeling choice of how you categorize these, right? This is just the specific one they chose. So let's continue. To predict the next interaction, we combine request time features from the current step with post-action features from the previous step. This blending of contextual and historical information ensures each token in the sequence carries a comprehensive representation, capturing both immediate context and user behavior patterns over time. Consideration for model objective and architecture. As previously mentioned, our default approach employs the autoregressive next token prediction objective, similar to GPT. This strategy effectively leverages the vast scale of unlabeled user interaction data. The adoption of this objective and recommendation system has shown multiple successes. However, given the distinct difference between language tasks and recommendation tasks, we have made several critical modifications to the objective. So let's see, this strategy effectively leverages the vast scale of unlabeled user interaction data. I guess like in a sense it is unlabeled in the way that the interaction data, nobody, has manually queried a data set for it and labeled it. But I think like in this case, it poses to a very natural self-supervised learning approach. Because like there actually is important information in the interaction history itself. So actually I'm still a bit confused when they say like this semi-supervised learning of what they actually mean. What is the unlabeled and labeled data in this case? Anyways, let's continue. Firstly, during the pre-training phase of typical LLMs, such as GPT, every target token is generally treated with equal weight. In contrast, in our model, not all user interactions are of equal importance. For example, a 5-minute trailer play should not carry the same weight as a 2-hour full-watch movie. A greater challenge arises when trying to align long-term user satisfaction with specific interactions and recommendations. To address this, we can adopt a multi-token prediction objective during training, where the model predicts the next n tokens at each step instead of a single token. This approach encourages the model to capture long-term dependencies and avoid myopic predictions focused solely on immediate next events. Yeah, I think that makes sense as well. It's definitely myopic to just want to predict the next item they would want to watch, right? Secondly, we can use multiple fields in our input data as auxiliary prediction objectives in addition to predicting the next item ID, which remains the primary target. For example, we can derive genres from the items in the original sequence and use this genre sequence as an auxiliary target. This approach serves several purposes. It acts as a regularizer to reduce overfitting on a noisy item ID, provides additional insights into the user intentions or long-term genre preferences, and when structured hierarchically, we can improve the accuracy of predicting the target item ID. By first predicting auxiliary targets such as genre or original language, the model effectively narrows down the candidate list, simplifying subsequent item ID predictions. Yeah, I mean, this is not something that like LLMs do. Like the auxiliary prediction objective is not. I would be curious to see like if this actually helps, or if this is just like, I mean, it makes sense if they actually want to use these auxiliary predictions in some way, but if they added them as an regularizer effect, we'd be curious to like see that this actually worked, right? So at some point they must have run into some type of overfitting issue, right? Because why would they want to regularize it? And so I would be curious to see a little bit more insight, you know, like what exactly did you run into as for the issue here? And then how did you evaluate if it solved it with introducing this type of regularization? Unique challenges for recommendations foundation modeling. In addition to the infrastructure challenges posed by training bigger models with substantial amounts of user interaction data that are common when trying to build foundation models, there are several unique hurdles specific to recommendations to make them viable. One of the unique challenges is entity cold starting. At NetFlix, our mission is to we can skip this, man. So basically, like they have an issue here where basically they need to figure out how they do for newly launched titles, right? So they have this incremental training and being able to do inference with unseen entities. So incremental training, let's see. Foundation model training on extensive data sets, including every member's history of plays and actions, making frequent retraining impractical. However, our catalog and member preferences continually evolve. Unlike large language models, which can be incrementally trained with stable token vocabularies, our recommendation models require new embeddings for new titles, necessitating expanded embedding layers and output components. To address this, we warm start new models by reusing parameters from previous models and initializing new parameters for new titles. For example, new title embeddings can be initialized by adding slight random noise to existing average embeddings or by using a weighted combination of similar titles embeddings based on metadata. This approach allows new titles to start with relevant embeddings, facilitating faster fine-tuning. In practice, the initialization method becomes less critical when more member interaction data is used for fine-tuning and dealing with unseen entities. Even with incremental training, is not always guaranteed to learn efficiently on new entities. It's also possible that there will be some new entities that are not included seen in the training data, even if we fine-tune foundation model on a frequent basis. Therefore, it's also important to let foundation models use metadata. Thus, our foundation model combines both learnable item ID embeddings and learnable embedding from metadata. So this following diagram demonstrates this idea. So I think basically what you're trying to say here, right, is that when we have a lot of data that people have interacted with a particular movie, we can learn a lot about this movie, right? Based on just interaction. So this is collaborative filtering, right? However, if we don't have data, we can't rely on collaborative filtering. So then we need to rely on content-based filtering. So this would be information about the actual movie, like what genre is it, what tone is it, what storyline does it have, in this case, what they've chosen. And then basically they create an embedding of each. But this is data that when they create the movie, right, they create these this information, this metadata of the movie that we can then use embeddings on. So this is on the content approach, content-based filtering. And then they have the collaborative, which is based on the actual interactions. And then what they do is that they mix these. So basically they're trying to say like, okay, well, we can't just rely on collaborative filtering, right? Because we need to cold start for many. So we can use content in that case, but we also want to mix them. So we have this mixing layer of basically this one learning of, all right, when should I take what into consideration? And they have some strategies of, we can initialize this, not just initialize it by random noise, actually initialize it by some type of average of the top X movies that are close to this one or something. So that's what they're trying to say here. And this is a very common sort of paradigm, which, combining these two into a hybrid recommender system. So yeah, to create the final title, we combine this metadata-based embedding with a fully learnable ID-based embedding using a mixing layer. Instead of simply summing these embeddings, we use an attention mechanism based on the age of the entity. This approach allows new titles with limited interaction data to rely more on metadata, while established titles can depend more on ID-based embeddings. Yeah, so that's what we talked about essentially. I think like the mixing layer will learn when it wants to use what. All right, so what are the downstream applications and challenges? So it can direct use as a predictive model. We can use this to predict the next entity a user will interact with. All right, so then it can be used as a predictive model, and they just say here, these can be directly applied to meet diverse business needs. And we can, I think this video is way too long now, so let's just try to summarize this. We can utilize the embeddings because the embeddings learned are very vital and important. We can fine tune with specific data. So this model's adaptability allows for fine tuning with application specific data. So we can later on train this as well. And then we can, let's try to summarize because it's going to be way too long otherwise. Basically they say that, scaling foundation models generally is a lot, leads to better performance. And so they trained a bunch of different ones, and they saw that, on a logarithmic scale, then it increases performance if you increase the size. I think if we look at the actual size here, relative model performance improvement, and then it's all a bit vague, to be honest. And then they were like 1 billion is a very small parameter size. So I would be surprised if the cap was only set to 1 billion actually. That seems like a quite low model size. And then in conclusion, our foundation model for personalized recommendation represents a significant step, creating a unified data-centric system that leverages large-scale data to increase the quality of recommendations for our members. So yeah, I think definitely as a whole, this is a very interesting idea. I think we've seen it work with LLMs. I think it should work on there. I think their idea of, let's not have thousands of models that we all need to fine tune all the time, and use a more a foundation model that is larger and has more rich information that we spend a lot of time on fine tuning and getting it really good. And then we can reuse that in smart ways, right? I think that makes sense. I think the knowledge cutoff thing makes it a bit trickier in their case because they have to constantly fine tune this, right? Which is not really the case for LLMs. Additionally, one thing that I think they kind of did a vague blog post. I really would have liked to go into more detail, so for example, like a challenge I can see with this is basically, so a lot of the interaction history is already built on their pre-existing recommender systems, right? Like if I go on to Netflix, like I'm going to use what I see, right? And what I see is based on their recommender systems. So I have a sense that like what this learned is basically what their like existing recommender systems have created, if that makes sense. So like in some sense, I kind of get an idea that this is a distillation. So I wonder if like the fundamental idea of training on just Netflix data is too limiting, essentially, because also that data is curated by a pre-existing model. So that's just one idea I have, like, that I would want for them to discuss a bit more on, because I think there's a lot more, like there's a lot of challenges with fine-tuning this way. And then also like on the modeling side, like just to see that the cap is here, that they find it to be at 1 billion, that seems to me quite low. And so I would be curious if they talk a little bit about sort of size here, because the general idea is that we scale data, but we also scale the models, right? Like DeepSeek V3 is a 700 billion parameter model. And so this is, compared to that, extremely small, right? And so I would think that on a Netflix scale, they would do something that's larger than 1 billion. Because, yeah. Anyways, other than that, I think the idea is very interesting. I think the blog post was cool. Link it in the description. And yeah, let me know what you guys think of it. And if you have any ideas. Again, thanks for watching. And yeah, hope to see you in the next one.